This is good.
Okay, our job today is to put together some pieces that we have developed here, and in particular, put this on both screens since it's so important. The thing we're going to do today is look very carefully and show the simplicity of the idea of two-state system and this machine as a sort of a logical, but also a computer. You can use it to calculate things, and dials are fairly precise. But the idea is that in a two-state system, you have the Hamiltonian, which is represented by this vector here, the crank vector, that's going to be applied to some state that has a certain spin that's pointing in a certain direction. So once you get that into your head, it's pretty easy to see what we're doing in the past, but today we're going to really make use of this. And the idea of having three angles to describe the polar coordinates and the turning of the crank, and those are called the axis angles, the Darboux angles. I'll mention the geometer Darboux a little bit later, but those three angles, which I have chosen to be italic Greek, the axis angle of Azimuth is a italic phi. It's the angle from the x-axis of the laboratory around to wherever this crank support is. So that's the azimuth of this crank vector, and then the elevation of that is measured off on this scale right here. So that's the italic theta, and then there's no r here, but there is how far you've turned the crank, and that's the thing that's going to be driven by time. The omega vector is really what we'll be talking about, but the omega times time is the uppercase theta. That's the third angle, the angle of crank rotation. So that's three angles to describe a state apart from its amplitude. This is its direction. The amplitude is another question entirely. Similar arguments for the actual thing that's the victim of this crank or time evolution operator, and that is the device itself with the spin vector attached to it, but the spin vector has three polar coordinates consisting of first the azimuth right here, and now this is a dial attached to the laboratory that's measuring this frame, literally an aluminum frame that holds the axis for the polar angle, beta. Beta rhymes with theta, so alpha's got the first letter A of the alphabet, so azimuth, and then theta, the polar angle for this spin vector. But then the spin vector itself has some rotation associated with it. The gamma dial, gamma I guess for gauge or phase, this is the thing that keeps track of the overall phase of the two-state system, and does it in a very mechanical way, and that's the reason we built this thing, really. And the reason Dudley Hirschbach wants to build one for Harvard physics department and chemistry department. Yes?
Professor, gamma is the one that takes care of the rotation of the sphere about its own axis, right?
Yes, yes. Very obviously so. I mean, this is the coordinate system. Eventually we're going to be using this to designate the rotation of a molecule. So this will actually refer to something that's in our living 3D X, Y, and Z space. But here we're in an abstract, I usually call it A, B, C space, and this is the laboratory that has that space, and then this is another space that's riding with the spin. That's something that takes a lot of people getting used to, because that's not the way spin's described in most of the textbooks. You see, it has that extra angle there that the others don't have. So that's what we're going to use today. We're going to, if I can just back up a little bit here to show what it is I want to do. First of all, I want to relate these two kinds of angles, the Euler angles and the axis angles from geometry Darboux, and the connection to a four-dimensional object, that is the complex amplitudes of the two-state system, psi1 and psi2, consisting of position and momentum in dimension 1 and dimension 2. So that's something we've already talked about, but it doesn't hurt to go over it again. And then we need a conversion between these two kinds of coordinates for various things. And we want to test that and then actually use it in rotating something. This is an object that's supposed to describe spin a half, even though it's living in a vector space that we live and breathe in. It is capable of tracking all the way through what the spinner does. And the spinner, as we've already mentioned, requires you going 720 degrees. That's 4 pi of rotation in order to return to origin. So we'll show a little bit of the real world 4 pi spin behavior as well. And then we'll go ahead and just apply this one more time to the individual types, A, B, and C of Hamiltonians. We've already looked at this once. We'll stop at this one and this one just to make a connection with this 4 pi business. And then the mixed types, that's something that's really important. And this is when, once you get two of them together, you see a spectrum that is an avoided crossing, has a direct point hiding in it. And you also get an idea of what it means to talk about invariant toroid for oscillators, those 4 dimensions. We can look in 3 dimensions of that and see some of the geometry that's going to. And then finally, the stuff that I really want to show here is how this connects to optical polarization, which is one of the most precise ways that spectroscopists are now using for all kinds of things, not just molecular spectroscopy and rotation, but solid-state physics as well. Very powerful tool now that we have a control of light, and very beautiful ways to control a coherent light. And we'll see how far we get, because I would like to once again bring these Euler angles and axis angles together to find eigenstates of a two-state system in a very physical way. And we'll see some strange things that polarization can do. Okay, without further ado, let's go ahead here. I've already said a few things about the angles here that we need. And now it's time to make the connection between the rotation that does it with a crank and the rotation that does it with 3 settings of the alpha, beta, and gamma angles. So if you don't recall how we did this in detail, why this 3 works and why we get this particular setting here, these are supposed to be links that will take you to the description of that. And the same thing goes for this link right here. If you have that on a computer, you can go back and review both of these things. But we pretty well take care of most of the details of that review with what we're going to do right here. Now the real point of this is, this particular slide, is that the Euler description, the Euler angles are simpler to form. That is, this is usually a simpler matrix to get than that one. And the idea is we're going to equate this one to that one because we would like to be able to describe the state not just with Euler angles but also with the Darboux. And a state definition is going to let us relate that, but the idea is that alpha, beta, and gamma make better coordinates of the state that we're talking about. They're better for physics, and astronomers use them to aim telescopes and the polarimeters that they have in telescopes. Whereas this one is a better way to describe the operation that took you to the alpha, beta, gamma angles, you see. So this one is better described as a set of group parameters. These are parameters of the actual action of going there. But they're so very different in looking and shape here. So that's the thing I want to make clear. Now, this is a key equation right here. Yes?
Isn't that how they mount many telescopes?
Well, there's a lot of things you mount this way. But the one that comes to mind of most people in this building is for solid state physics. It's called a gonometer. Gnomon means
A stick in the ground for judging shadows and
right.
angle.
But this is capable of doing all three dimensions, right? So telescopes are mounted like this, and then you have an additional, as a polarometer would to measure polarization. Obviously, you would do it with the axis on the axis of the telescope, pointing at what you're looking at, right? So that would you know, use either this or that set of angles. Yeah. Okay, okay. Well, anyway, we start off by saying, okay, here's an expansion. Always take a matrix in this two-state system and expand it in terms of the the A matrix, which is the Z. Now I've got them lined up according to Pauli's X, Y, and Z. And then there's the guy that's usually called 0. I put him first. This is the overall phase driver. But here sits the bilaterally symmetric B matrix. That's the X. Here's that the C that does all of the current carrying cyclic and chiral motion. We'll see a lot of that action today. And then this guy right here is just a diagonal matrix, a Z matrix, but we call it A for asymmetric diagonal. So it's this combination of these matrices with these coefficients right here that's important. And the same thing is true down here. Each of these 4 matrices, counting the identity, have coefficients that are associated with the geometry here. And all of these are multiplied by the sine of the crank angle. So that makes it fairly simple, but you do have the unit vectors that go with it that have the polar coordinates associated with x, y, and z unit vectors. So that's basically that's this matrix taken apart in a way that really shows the guts of it. And this one, most of the time you wouldn't need to do this for Euler angles, but here's where we need it in order to equate each one of the coefficients of these matrices with the coefficients over here. So that's what's going on in the next 4 or 5 so slides that we have here. So the very first one is the x1 component of our spinner. Okay, the x1 component is the real part of this thing right here. And you can see I could just take the real part of this thing and get the answer to that. Gamma plus alpha cosine, and then cosine beta over 2. Okay, but that's what we're seeing by connecting this coefficient right here with this one right here, you see. So that's our first equality, and it's just equal to the real part of the first component. That's the coordinate of the first component. Then there's the momentum, and I happen to do the second component's momentum first and put a minus sign out of the way there. But that's that. Okay, and then this one has, we're now equating the bilaterally balanced operator, the X, if you will, matrix, that's a Pauli matrix X, right here has a coefficient that is written down here, and so forth, you see. Then the next one is to get the real part of this second component, and finally there's the momentum of the first component, is the last thing that we list here. Okay, so this is a gigantic sort of 4-dimensional polar coordinate conversion going on here, because we are really dealing with 4 dimensions of the phase space of a 2-dimensional system. Those are 4 real parameters, and we need to then be able to get a function, say, of the alpha angle in terms of those 3, then the gamma angle in terms of those 3, and finally the beta angle in terms of those 3. That takes a little bit of arithmetic, and that arithmetic is on the following pages. So
Dr. Harter,
let's go ahead here to the bottom of this thing.
how do you take care of the third dimension in those matrices?
How do you do a third dimension of,
How do you take care of the third dimension of the rotational angles and all of that stuff?
well, here are the 3 dimensions right here, x, y, and z, right? And over on the other side, they're right here. That's the A, B, and C, right? And then the 4th dimension is this guy right here. So, as I've been saying all along in this course, we're not doing much with this one right now, but that's the generator of relativistic transformation along the direction that's described by these 3.
So,
Okay.
all those 3 dimensions are described by that 2 by 2 matrix up there.
Well, we are dealing in both of these cases here with the spinor base function, which is 2-dimensional, 2 complex dimensions. So we're looking at the most general state of a U2, unitary 2 object, which is a 2-level system. And we've got the 3 2-level systems that are most famous sitting on that 3rd slide down there, right? So we're either dealing with spin a half of a proton, say, that would be the first one, the MRI, right? And then polarization is the one we want to tackle today. That's the second one. And we'll mention the ammonia too, when we talk about the Dirac point, which is that. But you have to be aware that there's a connection here between this 2-dimensional thing, which is 2-dimensional complex, and real space-time, actually, which is what this is representing. But this one is capable of tracking this one, whereas just the vector by itself isn't. Vector needs to have a twist, okay, in order to finish the job. Does that answer what you're after? Okay? All right. So, let's convert. Now this is all in one page. If you wanted to do this step by step, where you look at each of these equations one at a time, that would be helpful. But I'm not going to go through the algebra. I'm just going to show you the results of that transformation. Okay. Here's alpha, beta, and gamma given as our inverse trigonometric functions, and I recommend using a tan 2 if you program this, not just a straight arc tangent. Make the thing into a y and an x and give those parameters separately. That's polar coordinate conversion. You need to do that twice to use this thing effectively. And then you go through and you play with these relations a little bit more, and you get the Darboux angles, phi, theta, and big theta, the actual rotation of the crank, in terms of alpha, beta, and gamma. Same time, this time using, again, an a tan 2 and an a cosine, arc cosine. Okay, so that's the result. That's what you can use to connect these two ways of looking at things. And the example that is going to be shown here, I'm going to take alpha equal to 50 degrees, beta equal to 60, and gamma equal to 70. We're going to start with a state that has that with this machine right here. And we're going to figure out what the phi is, the theta is, and the big theta is, you see. And so when you do that, you get that the little phi is 80 degrees. So I've got it, I would have to set this thing right here to an azimuth of 80 degrees. And then the theta here, that's this angle right here, I would be setting that to 33.7, and then I would actually do a turn here by 128 degrees We'll see pictures of this. And it's a little hard for me to do it with this one because the suction cups aren't sticking well enough to make it a precise thing, and you're too far away to see the things on the angle. So we'll play this. So that's the thing here. Now you test it, okay? You test this formula right here by sticking in 80 degrees, 33, and 128, okay? And what you get out, you can see there, if you use your calculator, it's good to say 4 or 5 figures at least. You get 70.007, and you get 50.007, and 60.022. That's the worst one right there for, you know, when you take an arc sine. Okay, so that's something you always want to do with something complicated like that, is right away test it out. Okay, and it passes to within the degree of accuracy that
So, Dr. Harter,
a typical calculator has.
ideally, do you want alpha plus beta plus gamma to be equal to 180? Is that what you want?
Alpha plus gamma?
No, alpha plus beta plus gamma. Do you want the sum to be equal to 180?
Oh, there's no, I wouldn't be playing any game there like that.
Okay.
All sum of all three.
They're not interior angles. This is
Yeah,
a
they're-
solid angle measure.
They're as you can see from the diagram of the alpha, beta, gamma, or just look at this machine here, they're all pointing in different directions, right? They start out with these two in the same direction, then this one perpendicular, right? But most of the time, they're 3 separate axes. Okay, so only that very special starting point, which I will kind of play with here.
Sure.
What I'm going to do is I'm going to just release this thing and put this thing at the starting point, and I won't be real careful with that, but the idea was if I were to put this axis so it was right where the y-axis is, that would set all the dials to 0. This one's going to be a little off, and then I apply this to the object, and then what I have to do, you see, is I can't turn it if it's like that. I'll only turn it. There's the doorway. That's the cut in the space of the Euler Angle world right there, you see. So once I get to that point right there, I'm free to go now, and that's what we're going to look at. We're going to look at a series of photographs of this thing doing this, okay? And let's just go ahead and follow it through right now, because what I'm doing right now, I'm halfway through a 360 degree rotation. There's 180 right there. We started right here with the crank sort of pointing up at the top there. I turn this thing, there's 90 degrees right there, and then I keep going all the way around until that thing's back to the top, which is about coming up right now. So there is a full 360 degree rotation. I have to push this thing with a little help here. There the crank is back. So I have just done a full 360. And you can see the machine is not home yet. This thing's on this side instead of this side, right? I have to do another 360 to get it back. So we need to discuss that thing. That's the 2-to-1 mystery that exists between the spinor world and the real 3-dimensional world that we live in. This thing is, in a sense, capable of living in both because of that topology there. And I'll show you that topology is really quite simple. So that's something we can start doing right here. There's the picture of the full, that's 360 almost, that's 300 degrees. 360 is right here. This particular thing has the beta dial almost hidden from the thing, and here the beta dial is in front. But the coordinate system's back. The coordinate system is back where it started. There's the y-axis right there. There's the x-axis right there. It's all the thing. Everything's fine except the Euler angles aren't back yet. And if you look closely at this, you can see what the Euler angle readings are at each point. This is a picture that looks better on a high resolution PDF than it does on a screen where the pixels are about a 1/16 of an inch here. So, but you can read the angles that I stopped at, and one of them was 128.68. That's the Euler angles of 50, 60, and 70 setting right there. Okay? And then there's the equivalent setting down here where the thing has gone 360 to get to that. And then it has to go again to get home. So that's an important piece of topology that our brains really don't contain this. Our brains do not have a good feeling for the fact that it takes 720 degrees to get things back home again, right? We'll see plenty of cases where the polarizations obey this. The optical polarization does this sort of trick. But I want to point out that there are a couple of other uses for this thing. One of them is build a device, a carriage that goes half as fast as you're actually rotating the table here. So you have to have a 2-to-1 gear there for the thing that carries the cable that goes to the turntable. You see, so you're supplying power to a rotating table, supposedly doing it in a way where the two wires don't get tangled up. They get twisted a little bit, but then they untwist. And that's something that's really quite remarkable. And where it's really testing it is to do it optically. That is, set up some prisms here that will project, so you have a glowing screen here with an arrow on it, and that image goes up and bounces off of these pyramids here and puts an image on a screen that's in the laboratory fixed. And as you rotate this thing, you get to see what it's like to live in that frame. This thing will stay fixed. And you can see if you have a dynamic system where there's Coriolis forces moving particles around on a turntable, you can see them moving as you would see it riding on that table. So this is a periscope that allows a stationary outside viewer to see into the rotating frame that appears fixed as the turntable rotates. I think this is extraordinary. This is a patent and isn't built very often. But perhaps it would be good if I just demonstrated it with a glass of water. It used to be when people demonstrated this, they had to do it with a belt, because that's the way Dirac described it in a thing. So they would rip their belt off, you know. Sometimes their pants would fall down, but that wouldn't stop them. They would go ahead with the demonstration with a belt, which is really quite hard to see. It's basically this. They would use a belt to imitate this, okay? But it's better that you just see that what I can do. Imagine this was a cup of water, and if I tipped it too much, it's going to spill, right? So I'm pointing the lid at you right now, and I'm going to rotate this by 2 pi and then some without dislocating my elbow or my shoulder. Okay, now if I do, please take me to the medical center that's down at the corner of College and whatever. Anyway, let me just take it here and rotate it to the point where it's pointing at you again. And then I do a little thing, I keep rotating it, and it's back pointing at you again. Okay, so it's been through 4 pi, 720, and I haven't dislocated anything. Okay?
Or poured water across your
Or
system.
if the thing was open, I can actually do it without dumping any water. Now the people that are really good at this are high school, what do you call the cheerleaders, right? Or the majorettes or whatever it is. And now they're male, and George Bush was a very good majorette at Yale. And they can do this with a flaming baton, right? Right? And so they know all about SU2. Right? They know more than you do, right? In that sense. And more than I do even. So I just wanted you to see, this is that 2-to-1 business coming here between these two spaces, spinner, 2 dimensions, and our space of space-time actually, X, Y, Z, and T, which is 4-dimensional. Okay, so the dynamics that goes with this, and let's bring this up to speed because we would probably like to do some animations that are associated with this. Remember we had the diagonal A-type motion. That's asymmetric diagonal. Okay, just that was a Hamiltonian, AD. Okay, so that consists of a sum of A plus D over 2, unit operator, and A minus D over 2 of what we call sigma A. This guy right here. And of course that's not what Pauli calls it. Pauli calls this sigma Z. Okay, and we have the Z-axis where the A is on this particular drawing. So this drawing is oriented to make Mr. Jordan and Mr. Pauli happy. Meanwhile, the other two dimensions are the ones that have the real dynamics associated with this one. All this one does is give you a motion in this direction that's one frequency, say slow, and in this direction the other frequency, which is presumably faster in this particular diagram. So I will not go over this one again. We've been to this particular motion enough, but it might help for our 2-to-1 discussion here to go ahead. There's the animation that would play if I did. Basically it makes a rectangle that's lined up with X and X1 and X2. So it's almost too simple. But here's the B-type motion there. And that's this one. This is the B-type dynamics. And this has to do with something rotating around the B-axis instead of the A-axis. And the B-axis consists of, and we got to get used to the sphere having a whole bunch of different points that are different types of optical polarization. That's the main topic of the day, is to produce that and discuss that in great detail. But right now we're looking at something that is going in the direction that's 45 degrees to X and Y polarization. And there's, at the opposite end of it is the orthogonal state. Just like the opposite end of this one, which has the X, has the orthogonal state X2. This is X1. So you could call that X and Y. I don't like to do that because we reserve X, Y, and Z for the 3 space. But there it is anyway, maybe write it in lowercase. So we're going to turn a crank here. A crank which is going to be going that way. Well, it's going to be going right-handed if you get over on this side. That's going to look like a left-handed rotation from this point of view on the positive axis. So that's the animation that this one will give you, presumably. So let's see how it's working there. There it is. Okay? Now, remember that there are eigenstates for all of these things. And if I click on this axis right here, then all I get is a very simple motion called a normal mode on that particular direction of 45 degrees plus sign. Or if I click on this axis right here, I get presumably a different frequency motion on the other normal coordinate. Okay, so these things play with each other that way. Now if I erase the paths and reset this thing, let's go ahead here and let me see if I could reset this thing with it located right at this point. I'll start even at 1 here so we make a pretty big picture. I'll start it right there and see what it does. And I kind of want to look at the thing. It might be good to slow it down a little bit. Let's see if we can do it at high speed just to save time today. So I start with that, and what I want to do is see what the phase is when it returns. Okay, so here it goes up to become Y polarization, and then returns. You see where it was when it returned? It was over here, right? Pi out of phase. Okay? So the thing returned on the negative side of this axis. And then it continues again, you see, through the whole dance. It started now on that side, it will finish now right on this side here. So there you get to see the effect of that 2-to-1 behavior. And if that was all you knew, you'd say, what's the big deal? Of course it's going to do that. That's just the way it works. And then I'm going to stop this thing, and we'll go to the next case here. And I'm going to go back to the lecture here so we can do that. The next one that we'll do, besides this one, is C-type. Okay, that is the one that I think is really easy to show. First of all, just by looking at this diagram. What's going to happen now is the crank's going to be on the C-axis here. Okay, and I'm going to start off with this thing now. Notice the two different colors. I don't know if you can see that. Sometimes people that have a color anomaly won't see that this is a bright red, and this is sort of a dull brown. Okay, is that coming through to most of your eyes? Yeah, more or less, right? Okay, so what happens? I'm going to just point my hand. Boom, 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 boom. This is Faraday rotation. Finally, I get over here. I'm at 45 degrees, going like that. Here I'm going like that. I'm always poking into the thing. But now, you see, as I come up this way, my poker's this way instead of that way, right? I started poking, you know, each time. That's the bright red. When I come around, the bright red's going to be on this side. I got to go all the way around like I did with the bottle and finally get back poking in this direction. So you can see the 2-to-1 topology really clearly from this. And as I say, it doesn't hurt to do it, of course, on the animation for this. And I think I can get that to go here rather easily. Let's see if it does it. There we go. So, this thing started here. The question is, when it gets over here, where's it going to be, you say? Now, here it is, having rotated halfway, but it still has to go the full way around, just like we said. And when it gets exactly to that point, it should be over here. It might make a liar out of me. There. And just at well, it's hard. We should probably do that in slow motion, but you would see that it does take this thing going all the way around, and it comes back half out of phase in the spinner space. Okay. Well, anyway, this is all stuff you do with just one of these things at a time. Okay, but the same thing's going to happen when we mix them up, and that's when physics gets really need this way of describing the power of this of describing these is the important thing.
Isn't that motion like if you have like a Mobius strip and you project a line, and then when you get to the other side, exactly they will be opposite?
The topology has connections, yes.
So it will be like a Mobius strip topology.
You go around and you're on the other side.
If I draw a line in this, like an arrow in this way, and I do this, exactly at the top on the other side of the Mobius strip, it will be at the opposites, like pointing the opposites. Yeah. The arrow.
There are what, 3 kinds, actually 4 maybe.
Well, it depends on
two-dimensional topology, right? You can have the projective plane, where the thing goes up here and comes back here. You can have the torus, right?
Oh, that one's more.
And then you can take the torus, instead of connecting it this way, connect it that way. That's the Klein bottle, right? So there are those are 3 kinds of two-dimensional topologies, and that's an amazing discovery in itself. Because we're just talking about two-dimensional space now. Here the space that we have is not so complicated.
It's just like a Mobius strip, because Mobius strip only really has one face.
Yeah, this is an orientable surface. That one's not.
The Mobius strip not.
Yeah, that's right. Before we go on here, what I'm I don't know how that one got up there right away. What I want to point out is what we're going to be looking at is the solution to a general Hamiltonian. Different number here, different number here. We'll stick with a complex number in general here, but let's just keep it real. We would have this. What we're going to see as an exact solution to this, of course, is two hyperbolas. But this slide somehow got out of order here. What I wanted to show with this is that high-order polynomial perturbations, this is the second order, actually first order, but second in potential perturbation, high-order perturbations really can't match hyperbole. You know, you've already gone up to there's second order right there, but then there's third and fourth. They push you along the line, but then they always deviate out. So this is something that you should keep in mind. That's why I was saying to the perturbation theory really is not a, let me get rid of the blue blob here. I'm going to pause this thing so I don't waste computer time and bring this back. Okay, so let's go ahead here. This is what we're dealing with if we include two of these at once. Okay, this is the simplest case. The A and B mixtures, A, D, and B really, but this is what we call the A matrix, and this is what we call the B matrix for the Hamiltonian. And really all you're doing here is by varying this right here, is you're looking at normal modes that are tipped. Okay, now here's the pure B symmetry, here's the pure A symmetry. Now we're not involving the complex guy. That's when it gets really funny. But I can take any two of these, A and B, A and C, or B and C, and gets similar sorts of things. But this is the easiest one. This is the one that doesn't involve the imaginary numbers. And I don't need to do anything fancy with the polarization. It'll always be straight line polarization. So basically what we're dealing with here is the A-B equator. And on the A-B equator, all of the orbits are closed. They're not open like the orbits that are in the northern hemisphere, which are open this way with a right-handed twist, or on the southern hemisphere, looking from this as the North Pole to the South Pole, where they are all left-handed. So bringing C in brings in chirality. But if you stick to the tropics, okay, stay around the equator, you never have to deal with this elliptical stuff, okay? And Lewis here was complaining about the changing weather of Fayetteville, right? Well, tropics, you go there, it doesn't change that much, right? To get between the two tropics, so, except for the hurricanes, the weather doesn't vary that much, okay? So, or the climate doesn't. So that is something we need to talk about here. So the basically all that's going to happen with C equal to 0, which is the case for this animation right here, is that I will get a set of orbits that look like that. We might as well run it, see if this one's working. Yeah, there it is. Okay, but what you can see is that if I click on this point right here, we've got a normal mode. It's just not on the axis, right? And the other normal mode right here is the same deal. It's a straight line. No big deal. Okay, it's something we can get a feeling for. Meanwhile, the two things that I've shown you is the spin vector on the top side of the omega thing, which is this one. That's the high frequency mode. And then the low frequency mode is this one right here. That's in the easy part of the potential where the topography lines are more separated. And this corresponds to a spin that is on the downside of the omega crank. Okay? So the real rule is here, and it's going to work for these C-type motions as well, is if you want an eigenvector, you're going to find both of them on the crank vector. That's a really important part of this thing. So the idea there is that if you have a particular state, and I'm going to make this thing go away for a moment. If I have this thing at a particular state, okay, all of these settings cause this thing to exhibit complicated motion. But if I can swing this thing, you know, over so that I can catch the spin vector of the thing, the spin vector, remember, is coming out of the north pole of that ball there. Right here, if I can get it right on that north pole, there's not going to be any motion allowed except for this gamma dial that corresponds to the twist of this thing. Now I didn't quite get it on, so this thing's going to shake a little bit. The alpha's going to move a little bit. The beta even's going to move a little bit. But if I got it right on there, these dials would be constant. So that's one mode of a Hamiltonian that has this crank, and the other mode is turned over, the upside down. Okay, and it isn't very easy to put the crank. The same thing happens. So the high frequency mode might be that one, and then the low frequency mode would be that one. Spin up and spin down. That's what we're going to see as we go through the rest of this talk. Okay? All right. Well, let's get to it. And it does get a little bit hairy here. Let me go ahead and pause this one to get back to the presentation, which is there. And go ahead. And so what I would like to do is say a few things about just the A and B mixtures. So we're talking about this Hamiltonian right here. It's a very simple secular equation. Okay, it has no trace. So you just have epsilon squared and then the determinant of this thing, A minus A squared minus B squared. Okay, minus A squared minus B squared. That gives you a hyperbola. The actual epsilon, forget that right there, it's just a square root of A squared plus B squared, plus or minus. So as a function of the B parameter, these are the curves that describe the energy values coming from this. This is an equation for a hyperbola for a particular constant value of A and a variable, I'm sorry, this is a constant value of B and a variable A. Coming this way, I presume you could plot the rest of it and it would be a different thing. But anyway, right there, it's the symmetry point. And then here, I make A less and D bigger. Here I make A, the parameter A, bigger and the D less. We're talking about, let's see if I've got this. Yeah, I should say, what I could do, of course, is raise the A and lower the D, or lower the A and raise the D to be on the two sides here. So that's what I actually had in mind when I was drawing that. But in any case, the idea is you're varying the electric field, and you're talking about an object that has, well, actually thinking here of ammonia. I'm thinking of the nitrogen being on this side. That would be the extreme case for the vectors, where the eigenstate for that particular value was something lined up on the y-axis and then lined up on the x-axis. And then on the other side, it's just the opposite. The low one is lined up on the y-axis and the high is lined up on the x-axis. So imagine you have a positive E field here that would tend to drive the nitrogen to that side. Let's suppose the nitrogen has a net positive charge accumulation around that nucleus. So an electric field applied to this thing would tend to make this state. Whereas if there's no electric field, then it's balanced. Right here we have a B-type system, with no A, 0 right there, if that's the situation, then you have equal amounts of wave function, that is, equal amounts of probability to find it on this side or this side, and that's true for both of these where they're in phase, and here you know the excited state is out of phase. So these are the actual sort of nitrogen orbital wave functions that you would sketch. This would be the ground state where it's plus phase. That means you have some more wave function in the center between the hydrogens than you would on this one, where there has to be a 0 in order to go from plus to minus in phase. So the nitrogen would have essentially 0 probability to be exactly between the hydrogens, whereas this one has a very robust probability to get into the middle of the triangles there, and that's this state here. So that's what we're talking about, and then we apply an electric field to the thing. If we apply it slowly and we start in the ground state, we'll just bend it over until you have a very large population on this side. And then you slowly bring it back, and then start the field going the other way. Then you're going to drop down to this state right here, where the nitrogen is almost 100%, approaching 100%. On the x-axis, that means on the left-hand side, the downside, if you will, of the ammonia molecule, and this is the upside of the ammonia molecule. So this is our third type of two-state system, the one that changed our culture as far as having lasers and all kinds of wonderful things like that. This is the idea of the Ammonium Lasers. It's a skeleton of the energy that was being played with by Charles Towns. And his trick was to realize that if I could get the thing over here and then have it go through a chamber that would have the field turned around, so all of a sudden I turn the field around. Well, it can't go around the curve. It just, you might say it has inertia. It's like a car being driven too fast into a curve of a road. It's really going fast. It's just going to go this way. That's a very rough way to say what happens. So that this way, Charles Towns could very quickly take the ammonia that he had very slowly taken over to this side and drive it here, so he became in the excited state. And then he had a coherent population of microwave emitters. That was the microwave emission by stimulated emission of radiation, the maser. The maser is based on just doing that with this diagram. So as I say, this is population inversion. The first time it was done, really in large scale, was in 1953, based on this incredibly two-state system. A lot of simplification going on here, but the basic idea is what to say. Now, one of the things you should realize about the symmetry of this, and that is, if I apply this transformation here, symmetric, anti-symmetric, to this matrix, it has the A's on the diagonal and the B's off the diagonal. It's kind of a neat thing that happens. Just going here and multiplying the matrices together to get that transformation. So I get this thing, 1/2 of, and I get by putting this guy here, I get a 2B, a 2A, but that just comes down to this. So this transformation, this unitary transformation of the Hamiltonian we're working with, takes us to the eigenstates. And the eigenstates have plus and minus B, and we'll presume for the moment that if A is small, then we're right in this neighborhood. There's the plus B state, the high mode, and there's the low mode right there. So this is a transformation from the eigenbasis that goes with asymmetry, which is out at infinity plus or minus, where I have all of my wave on one, localized on one or the other positions of this thing. And that's what's being drawn right here, the up and the down states that you would get if you ran the electric field way high or way low. And it would be true here. It's just that when you run the field way high on an excited state, it says, I'm going against you. These are the contras, you see, the excited state. Here, the ground state, oh, we'll just go along with whatever the political winds are. But here, they're the rebels, right? The excited states are the rebels. And they'll fight you. If you run your field higher and higher, it just gets more and more population against the field. Vice versa, you run an electric field this way, well, this one just docilely goes and gets stuck on that side of the field, wants it to be, and this one is the contra. You see, it's PHYS. That's the typical thing that waves do. This is a very simple case where you can see that contra versus non-contra behavior.
Dr. Harter, the matrix that you have over there, like 1 over root 2, 1, 1, 1 minus 1, is that
that's the diagonalizing transform.
That's a diagonalizing matrix.
Yeah, if you started with a matrix that didn't have any electric field,
Right.
okay, it would diagonalize it. There it is, you see. It took the B's off the diagonal and put them on the diagonal.
Right.
But in so doing, it took the A's off the diagonal here and put them off.
Yeah, well, that's what is
Isn't that
confusing
cool?
me, because that's confusing me because when you make a unitary transformation, you expect your resulting matrix to be diagonal, right? With the
You hope it is in the case, and we really hope as group theorists, that the transformations we get with our little projectors, right,
Yeah.
are going to give us a diagonal matrix because those are the energy eigenvalues we're going to
Right.
get paid for, right?
Right. Yeah.
Okay? But of course, if you do it to this matrix right here, you better hope that your pay dirt is getting the B's on the diagonal, right? Because it's going to take the A's that are already on the diagonal and put them as far away as they can get.
So once again, so could you once
You
again
need to see that. Two kinds of symmetry, right?
Yeah.
One side the A type, the other type the B type.
Right.
And then in between we've got, real world, this here and
So-
this here.
So physically speaking, your A's are your energies and your B is the perturbation, right?
I would call the B a tunneling or sneak factor. I often use the letter S.
Which is weak compared to A, right? That's the assumption that you make before you solve the problem.
Well,
or is it not the case always?
if that's true, I can use perturbation theory, right?
Right, yeah.
Okay? If it's true that A is really big,
Uh-huh.
okay, I'm either here, right, with a positive A, or I'm over here with a negative thing, that S isn't going to have much effect, right? Best I can do is get tiny little bit at this point, right? And perturbation theory would give you that.
Right. Okay, so here there is no need
It's
to
here,
assume that
it's here where you get wholesale transfer, tunneling between these. Here's where the nitrogen atom is not in one place. It's both here and here. Wow.
so
You
it's a
see,
super-
not a particle. This
Okay.
is a molecule that is not
So
classical.
that's a superposition state, basically.
It's a superposition of being here and here at the same moment. Yeah. A lot of physics in this little guy, ammonia. And we're not even touching, wait till you get the rotations and the vibrations going.
Could you,
It still happens, all this stuff happens.
could you give me a reference to this one in the textbook? No, lot more details, like where you would have described this problem in a lot more detail in your textbook.
And you shouldn't just read what I wrote, because this one is well described in Feynman volume 3.
Okay.
Just do that and look in the index for ammonia. Yeah, he doesn't have quite the diagrams I do, and there's no group theory there, because he didn't really think that much about group theory. But he didn't need to. I mean, here's your circular equation, right? Don't need to do anything. Yeah. Except show the symmetry, and the symmetry is an important thing. And the notation is a little different. I call this dipole moment times electric field. That's what the A really is. Those are the units of it.
But-
MKS is.
But Dr. Harter, this has been discussed in your textbook on quantum theory for computer age, right?
It's there. Yeah. C2.
C2.
Yeah.
That's-
C2 sub A, C2 sub B, C2. That's all in the unit 3.
Oh,
I think.
unit
Isn't that right? I'm trying to think. Yeah, it's unit 3.
There's the text detail. You can drill down. You can do a search.
Yeah.
Yeah, you could probably just put in ammonia, right? Just like you can with Feynman's book. And by the way, Feynman's book online.
Oh yeah. No, I have
Yeah.
a copy of this book.
Yeah, they, you know, you don't have to pay $100 anymore. And the errors are correct. You have a lot of errors. That's what you get for high energy work, right? That's the way I justify all the errors I've got.
I hide behind it too.
Yeah. Okay. Now, that set of hyperbolas,
So Dr. Harter, one last
that's
question.
what it looks like, right?
So one last question. So here in this problem, B can be comparable to A. The strength of B can be comparable to A, right? There's
Yeah, here's where I get to look at both A, so there's the electric field axis, right? And this is the tunneling amplitude axis, B. This is the B axis, this is the A axis, this is just the energy we were plotting, right? So we got two hyperbolas. I picked a certain value for the tunneling. That doesn't change, right? It does as you go to higher states of other electrons and stuff, right? But for a given binding, and you don't need to think too much, the tunneling is constant. Okay? Not only that, it seems to remain constant in extreme fields. That's what's really kind of surprising. But it does. That sort of thing is seen elsewhere. So here's our ground eigenstate right there with no electric field. But as I turn the electric field on and start to drive it this way, I sink in energy, right? If I was in excited state though, and I drive it, I increase the energy. It's just the opposite. Okay? Those are the contras, right? They're always doing the opposite of whatever you're telling them to do, right?
So no matter how much I turn my electric field, I will always have that superposition of states of ammonia, right?
The idea being, though, as you get down out to here, it's almost 99.9% in the direction of the field. The ammonia is, you know, on the top side. You see, for, you know, a field about this big, right? There's still a little bit of wave back there on the downside, but the upside is got most of it, right?
What about the upper?
Just the opposite. Just the opposite. And they're out of phase.
But they have the same probability, right?
Going the other way. Now, the 99% of them are against the field. Isn't that wild?
That doesn't seem very intuitive to me.
And this is something Feynman explains quite well. He doesn't use the contra language I do, but he should have.
But yeah, go ahead.
No, go ahead.
Is there anything about the structure of ammonia that makes this possible? Has it got to do with the structure, the molecular structure?
Yeah, it's kind of
ammonia?
interesting. If you take if you go down the periodic chart, what's the next one? Astatine or something? I don't know. But you make put a phosphorus or something else there. It takes thousands, millions of years to tunnel. It's essentially a classical molecule. But NH3 is a quantum molecule. And then if you use halogens, again, millions of years to tunnel. So it's classical molecule. So, you know, we get to see this just in very small cases.
So
yeah, Al.
What is the observable difference between a quantum and a classical molecule? What differences in behavior would there be?
If you shine in light at this tiny tunneling field, which is about what, 45 gigahertz, something like that. Forget what the tunneling splitting is. It goes crazy, whereas others don't. They don't have those tiny tunneling splittings that make the molecule absorb in a crazy way, make a maser.
Observable difference in how it reacts with other molecules or anything?
There would be if you could study the reaction in detail. And I think people are doing that. If you did it in a molecular beam, you could set the thing up into one of the, so it was really pure in a particular state, and then have it do its chemistry in a collision, you would probably find some real anomalies. But most of the experiments in chemistry aren't that sensitive that they can see. This was not something that was discovered until spectroscopy got to the point where you could see the doubling of the, all of the lines, all of the basic rotation lines were doubled. And that is just crazy, and then you shine light on it and it goes, makes a transition that later became our maser. Okay, what
Dr. Harter,
showing.
could you go to the previous slide where you had the previous slide where
This
you had
one?
no, here,
This
on the left side, figure B. So where you have expressed your states plus and minus as the superposition of the base states, the 1 over root 2 on the top and 1 over root 2 at the bottom of that figure there.
This one.
Yeah, that one. Yeah.
Yeah.
So that gives you the amplitude for the molecule to be in both the places, right?
And the square of the amplitude is probability.
Yeah, that's
So it's 50-50, 1/2, 1/2, right?
yeah, right. So that's the amplitude for
But
nitrogen.
so is this one,
Oh yeah, right. Yeah.
right?
Yeah,
The probability is the same, it's just that their signs change.
That's the amplitude for nitrogen.
Yep. Yep. And it really is, you see, thinking of waves as oscillations, it really is the difference between this motion here and this motion, the excited state motion here. I mean, that's the real point of this course, is we have mechanical analogs for these things. If you're willing to stretch your head a little bit, right?
Oh, like you mean to say in-phase oscillation and out-of-phase oscillation?
Yes. This is the anti-symmetric, this is symmetric. Remember when we did our C2 character table? We draw at the top row phasors in phase, right? And then the next row down, well, actually it was that way because this was always the one on the left, right? So that first character table, C2 symmetry, that's where we have the matrix that you see in the picture right there. But let me go ahead on that one to this point right here. There's this matrix right here is being diagonalized by this, right? And that's the character table for C2, right? 1, 1, 1 minus 1. That's what you've got over here. 1, 1, 1 minus 1. So, I don't know, does that help to have that connection? Or does it just confuse it? Because it should help. Because that's where the symmetry is exerting its influence in making these states that are very definitely symmetric and then very definitely anti-symmetric. Even with pretty high fields, I go pretty high fields, it doesn't change that much right here. It's only the second order that you start to say, oh, okay, I'm going to get over and be on the one side, right? I'm going to polarize. And just say, hell you, I'm going to anti-polarize, right? That's what the excited state says. But that's all after a second order, right? This is a parabola down here, right? And that one points up, this one points down. And that's the one that you mostly deal with because you're almost always getting in the ground state. Towne's genius was to say, no, I'm going to work with excited state. I can polarize that, I can polarize the heck out of that. And he did. And that's where the maser got going. Does that make sense?
So,
Very deep piece of physics here. Changed the whole culture, right? Think of all the things we have now that we wouldn't have if we didn't have coherent light. Back in the dark ages, right? Dark ages of 1954, 55, right?
Dr. Harter, so when you plot the energy, I can see that it's a hyperbola, but how do I see that algebraically? Is there a way for me to get the equation of an hyperbola from?
Well, this right here,
Yeah.
okay, with B constant,
Oh, okay.
right? And varying A, okay?
Right. Yeah. Okay. Yes.
The other way to write it would be to go A squared plus B squared is equal to E squared.
Right.
So if that plus sign was a minus, you get the
Yeah.
circular.
Well, then you get an equation of a circle, right? A squared plus b squared equals e squared. It's a circle.
But you bring it over on the right side so that you get x squared minus y squared,
Oh, right. Yeah.
okay, equal constant.
Because you fix.
That's the hyperbole you're used to, right? Better get used to that one too, because you see it a lot, right? Okay, any other questions about this? These are all good questions, and this isn't a subject, a lot behind it. And then a lot after it, right? All of the laser stuff that came after that.
So,
Just an explosion of work.
is there
A
any,
result of him getting the counter-ammoniums to polarize.
is there other molecules that we know which exhibit this behavior?
There's a whole bunch of them. They're called floppy molecules. And usually it involves methyls that are rotating. And some of them are sort of teeter-tottering as well as rotating. We're just beginning to barely scratch that surface.
What about NH4?
H4. Well, H3 is already weird enough. H3 as an ion is quasi-stable, and that's what Takeshi Oka has spent his whole life looking at, simply because it exists in outer space. We can take spectra without having to go to the laboratory. It's already happening. If you could go out with your eyes tuned to the microwave infrared region, it would be an amazing sight. But fortunately we can't, because it'd make you sick to your stomach too, probably. Okay, this is something that I thought, just for the fun of it, these two slides that go with this is what I call invariant toroid, just to make a point that we have a mechanical analog, and we're talking about trajectories in a oscillator space, but we've left out, the thing that we've left out of here with this C-type motion. Okay, C-type motion is when you go around on the Stokes sphere with your spin vector circling the C-axis. But if you circle the A-axis, remember, we get a rectangle that's not tipped. If you circle the B-axis, you get the same thing tipped by 45 degrees. And if you pick axes that are out in the middle of nowhere, well, then you get some pretty complicated behavior. And that's what I want to spend the rest of the lecture talking about. I want to talk about, well, AC types, but ABC types. Obviously, I can rotate this a little bit, and this will morph. These are just the plots that you get, and we're going to look at some of those in some more detail. But one of the things that I did that goes with this is to plot them in 3D using not just x1 and x2, but also x1, x2, and p1. So this is a three-dimensional object, and therefore, if you have these on your computer screen, they're usually about eye separation apart from each other. Go down and get your right eye looking at the right image and your left eye looking at the left image, and just sort of relax and pull away. You should see this in 3D. Even the little thing up here that shows the Stokes vectors is in 3D. So you can see what type of ABC motion each one of these is making. And what's happening there is there's a coordinate system on this donut-shaped object. It literally is a four-dimensional torus, and you're looking at a projection of it. It's a torus that has a hole this way that sort of closes off as a hole opens up in this direction to make this. So these are trajectories of things that have, well, some properties we're going to talk about. This is ABC motion, and there's a simulation that goes with this too, which I'm going to skip because we can talk about it in a way that's clearer. This one doesn't make really clear what's going on. Anyway, these are just something that would be of interest to someone that's just doing classical mechanics to see what oscillators can do with all three of these parameters, A, B, and C. And these curves here have a definite slope, and that's indicated by, if you look closely, 2 to 1 or 3 to 1, or the various winding numbers that are assigned to those objects there. So that's all well and good. Now this is a typical animation you get. This is a torus that's open this way, sort of, and open this way, sort of. But here it's just a trajectory. It's flat as a pancake on the screen there. Nonetheless, it has an intriguing look to it. So that's what we're going to study a little bit here. Okay, now the point of all of this today, because it's so important that we get used to understanding polarization more deeply than it usually is presented, is that there are these two ways to describe the motion of an electric vector. That's what this is. This is the trajectory of the tip of an electric vector of a plane wave coming at you with, in this case, some phase other than 0 and pi between the x-axis and the y-axis, what we call x1 and x2 in all of the stuff we've done so far. So this is the real part of the spinor components. The spinor components, of course, x1 plus p1 times I, and x2 times p2 times I. In other words, real and imaginary parts are position and momentum in the two dimensions. That's our spinor basis, and the analogy we've made is to bring that spinor or spin a half down to a place where you really can point at all of the geometry that goes with it. That's the trajectory that's being made, and we need to discuss that. But what's so neat is this entire trajectory with all of these angles and its geometry is a single point right there on the Stokes space, in particular the Stokes sphere. So this is the Stokes vector pointing to a point on the sphere, and the idea would be that the sphere would have a radius equal to the intensity of the light. Then this is this thing that has a radius, an outside radius that is the square root of the intensity. So once again, this is the square root, this little two-dimensional complex space, this U2 space right here, is the square root of the ones that we live in, the three-dimensional space that we live in, that Stokes invented. So you see, the thing about polarization is that the mystery switches from the space that we live in and think it's not mysterious to this space right here. Now this is the one that makes sense. This is very real to someone that knows optics and is worried about polarization. We're really talking about an electric vector. We know where it is. Or if you're doing two-dimensional oscillator mechanics like Brad is doing, like for MAD, this is very real to you. This representation is crazy, right? The 3D is the crazy part of polarization theory. But it's the simple part. It is simplified. It's taken this whole thing and reduced it to a single point. Every point on there is another one of these. And the equator, the A-B equator, they're all flat ellipses. Just back and forth, right? So that's a very singular region, the equator, the tropics, where the weather never changes, right? You don't have any opening in the ellipses. Well, you have a little one, it just come up a bit, but it's tiny, right? Okay, so that's something I want. And the connection between those is so beautiful. It's a 2-to-1 connection. For example, this angle right here, this slope, phi, that's an Euler angle. This phi is not the phi that we work with. It is an italic phi, but it jives with optics literature more than anything else, and then the alpha's an Euler angle, as we're going to see. Take this angle and double it, this azimuthal angle in this space, and double it so that it's not alpha over 2, it's alpha, it's not phi, it's 2 phi, double it, and it's the azimuth of this of Stokes vector for the Stokes vector that goes with this ellipse, okay? And then what's really cool still is if you take this angle here, which I've written as psi, it's the Euler angle beta over 2. So double that, you get 2 psi equal beta. That's the actual elevation, polar elevation, equatorial elevation. Now the beta that we're going to use is going to be the off of the c-axis. That's where polar angles go, right? They're always measured off of the axis as opposed to off of the equator. But this one is measured off of the equator, just as this is measured here. Now, this one I would call the Faraday angle, because Faraday was the one that realized that the polarization could rotate by some angle in liquids that have optical rotary power. That's what the optics people call it, right? You put in a certain polarization and it comes out rotated because the molecules all have chirality of some kind. So you can measure the chirality of a molecule just by looking at the polarization that goes through it. That's really cool. So you measure the Faraday angle, and it can be a appreciation of, you know, something you really can see, and that is part of the description. But then the other part is, how elliptical is it? Is something else happening? Nobody has a name on this one. Okay, so put your own name on this one. That's the elevation here, you see. And if it's big enough, if it gets up to 90 degrees, you got circular polarization. But all along here, you've got elliptical, you see, like this. Okay, so this is what we're working with. This is what we need to understand really advanced spectroscopy. So there's an elevation angle there. That's going to be the beta Euler angle associated if you use the c-axis. Okay, it's the complement, pi over 2 minus of the beta that we're looking at here, which is actually weird because it's an elevation off the equator. That's non-standard. Astronomers take precedence in most of these angular things. And then the azimuthal angle, that's an Euler angle right there. As I say, alpha. We're going to use that one today. The red stuff, we're going to work with the red stuff for the most part. At the very end, I'll show you how to convert to the green stuff, which is the beta sub c. But in any case, here's the Faraday angle, and here's, I guess, the aspect angle. It measures the aspect rate angle of the diagonal of the ellipse relative to its major axis. And of course, you could use the angle as a complement of that. All right, so you get an idea that polarization theory, that is ellipsometry, is what this is called. How many people have heard that terminology? You've heard of it? Anybody else? Yeah, can you imagine you have a whole subject that's just devoted to ellipses. I do ellipsometry, right? Sounds so poetic. Okay, all right. Let's go for it. Now, this is the ellipsometry equations that I would recommend that you learn first. The ones that don't necessarily use Euler angles. I want to do this one first because it shows what most people would do. If you go into Jackson and look at what he's using to describe polarization, it's something like this. It isn't quite, he's got a little bit screwed up. But the idea is we want to make a connection between these 3 or 4 parameters here. We've got a phase lag or lead. Those 2 quantities are negatives of each other, so they don't count as separate parameters. But we do have an omega t, that's the like the gamma, only it's overall phase that you would have for the beam. And then 2 amplitudes, x and y basically. x1 and x2 are amplitude 1 and amplitude 2. Okay, so this is the most direct, bare bones parameterization of polarization. No fancy Eulers, no fancy Darboux, none of that. We're on our just a simple quest here. And I am using what I use in my classical mechanics course to describe polarization. Or orbits in a two-dimensional, in this case isotropic oscillator. Okay? So in a box here I have x1 versus x2. That's the thing that's going to have an ellipse. And you see there's a whole bunch of other ellipses hiding in very fine lines there. And we're just going to make one of them, and then we'll show them all for every 15 degrees of an angle that is the rho 1 angle here, the phase lag angle. And right now, we're looking at a total phase lag between x1, that's this axis right here, and this is p1, that's the velocity of the x1, divided by the frequency. So this makes a circle, a phasor, for the first coordinate, x1. And then down here is the similar one, but this one is tipped over so that it matches the x2 axis. That is, I project off of what's going on the ellipse over to the real part of the phasor, which is right here. So this is x2, just like this is, you see. So these two are the same axis here, and then this x1 right here is the same as this axis here. So those are the two real axes. And then the P1 and the P2 are over here, but turned so that they match. This P1 matches that P1, this P2 matches this P2. So you get both the position and the velocity plots out of this. This position plot here will have an ellipse that's just like that, but shifted in phase. By, well, 2 hours on these clocks. These are clocks that you can click onto that will actually tick for you on the web. What we're doing here, you see on this clock, is we got 12 o'clock here, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. So if you're used to looking at a clock, this is your baby. And then this one right here is turned on the side, you see. There's 12 o'clock, there 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, you see. So what we're showing here are the total phase lag of what's going on number 1 phasor versus what's going on number 2 phasor. Number 1 phasor right now is at 4 o'clock. It's 4 p.m. on psi 1 time. It's a psi 1 phasor, okay? Over here, it's 2 o'clock, 2 in the afternoon. Almost time for this class to be over with, right? It's supposed to be over with before that. But anyway, this is 2 p.m. You see, you got to look at the clock from the side. 12 o'clock, 1 o'clock, 2 o'clock. So you see, there's sort of a mean time for these two phasors. It's right halfway between it, and that's why it makes sense to have a phase lag rho 1 and a rho minus 1, and split the difference between these two with that. That then makes it easy for us to follow this thing as time goes on. So here we are, it's 4 p.m. there, it's 2 p.m. here. We're talking about a 2-hour lag. That's 60 degrees, okay? Each hour is 15 degrees, okay? So then it ticks, right? Tick, 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 tick. This one now at 9 o'clock. This one's only at 7. Remember, this is 5, 6, 7, right? Tick, 10 o'clock. This one's advanced to the 8 o'clock, okay? Tick, tick. See what the velocity and the position are doing, right? So this is really a good way to get used to these things. And where this one touches the axis, we put a number down. That number is a key way to indicate where you are on your phasor, okay? Because if I come across here, I can look and see what the phase lag is based on that one, because I know where that one is. It's at an extreme point. This one is somewhere off of an extreme point. That's a good way, a good figure of merit. And then finally, tick, tick, tick. There's a whole bunch of them. just to see what you get for different phase legs. Okay, so this is something that you can play with without even going on the web. These are all the slides in this particular thing. I haven't gone on the web. But if you do go on the web, here's the thing to click, and then you can set any of the various things. And what's interesting, of course, is to have this phasor smaller than this one, or vice versa, and see how that works. Because then you get a rectangular diagram of some kind there. Okay, now, I want to turn this into Euler angles. Okay? Here's my x1, p1, x2, p2 that we calculated the very first thing today. Okay? And here's x1, p1, x2, and p2 from the rudimentary phase thing. So we're basically equating this to that. So all of them have this generic form of position and momentum, position and momentum. This funny kind of natural momentum that has the same units as the position does. So I do this. I just go through this thing, picking pieces of it out in a step. Okay? Writing equations that match. This guy has to match that guy. Okay? So there's basically the answer. Alpha equal 2 times the rho 1. The overall phase, well, that's 2 times the omega 2. That's 2 we're going to have to deal with. Okay? And then the tangent of beta over 2 is the ratio of the amplitudes. And this A here is the sum of the squares. That's it. It's not a very hard conversion, not like that thing where you had to go between Euler and axis angles. Okay, so here's just another polarization thing. But what I want to do is I want to actually get eigenstates and do the polarization studies of them. Now this is a little busy here. I should probably have broken this up, but we were struggling with this weekend, so I laid it all out here. This is the first time I really got a clear example of what I'm trying to show. Here's the Hamiltonian that we're going to be given. Okay, I just picked this one because it's one that will give us 60-degree angles. Actually, in this case, 60 and minus 60 for the Euler angles. But what I'm doing here, of course, is the same thing that we've done ever since we took a Hermitian Hamiltonian of the general form A, B, C, D, with this being A, this being D, this being B, those two numbers are equal, this being C, those two numbers being minus of each other, okay? And in this particular case I have a plus sign up here, which is unusual. Usually the minus sign for rotations and this thing are up in the upper left-hand corner. So that's when you spot the plus here, you got something different, and that is that the 3/8 is minus 3/8 that we're talking about here. So I've written here the components of the crank velocity vector. A minus D, 2B, 2C. Remember, that's the big angular. The little angle is half of this. Okay? But these are the numbers for the big one. Okay? 1/2, square root of 3 over 4, and minus 3/4. Half of this, I should say 2 times that 3/8 that's sitting there. So far, so good. And then, using the a-axis, this is the polar coordinates. The cosine sits on the a-axis, then sine theta sits on the other two with a cosine on the sort of x-like axis and a sine for the y-like axis. So this is z, x, y, if you were using Pauli's notation. But we take a first instead of z and go for it. Well, this gives us here, if a spin vector were to have Euler angles equal to the axis angles, what does that constitute? In other words, here's the crank that's out there spinning the spin vector, right? But if they're on top of each other, they can't spin it. Can only twist it, right? And that's a phase is getting changed. We don't care about that. We care about the polarization, right? So that's, once again, this message. Each eigenstates have their S vector along, that's usually the ground state, or opposite, that's usually the excited state, it's going to be the opposite here, I think. And this derives their Euler angles and the beat frequency. Okay? So, my spin vector here has got to match this guy. So, Euler angles and axis angles have to be equal. There's the Euler angles, they're the corresponding axis angles, right? That's the trick to find an eigenvector for a two-state Hamiltonian. Works every time, has to. And then I can do a square of those guys. That'll be my omega squared. In this case, it comes out to be 1. We just made that as a special for today. So, the Euler angles, I'm going to figure out what those are. Arc cosine of 1/2, that's 60 degrees. The alpha is the tangent of y over x, okay? Y is our c, x is our a, okay? So that minus 3/4 comes out here, and that guy, you just divide those two right there, so that I get the cancellation of that and a tangent for the azimuth. So the azimuth angle is minus 60, okay? All right, hyperbolic, atan of thing. And once again, you program this stuff, don't use arctangent, use atan 2, right? Where you have to put two variables in. That's polar coordinate conversion and won't kill you by getting the wrong quadrant. Okay, so then the spin 1/2 vector, now that you've got the Euler angles, 60 minus 60, and we'll leave gamma out of this. The overall phase is not being specified here. We're just interested in the state without worrying about that. That's the guy that we calculated as a generic state, so I only have to put my alpha in. I have to put in my beta, expand it, okay? And then stick in these values, and they're almost all over 2. So I end up a bunch of 30 degrees, sines and cosines. And there's the actual value, square root of 3 over 2 for cosine 30. Sine 30 is 1/2, okay? Sine changes signs, look at a minus 1/2. Another sign right there. So I end up with 1/4, 3/4, blah, blah, blah. This is my eigenstate. This thing. Okay? So what kind of ellipse does that make? That's really what we're interested in right there. Now, we also know what the slow mode frequency is for this. This is the fast mode frequency here, omega 0, which we haven't really looked at, but that's the A plus D that isn't shown here. Okay. A plus D over 2, remember, is the overall angular frequency. So we're taking our beat frequency over 2, this is the omega thing where you use a little frequencies, the ones that go with spin 1/2. This one is A plus D over 2, which is 1/2, plus omega over 2, okay? The omega is 1 radian per second, I suppose, but we're keeping the units sort of out of this. That's 1/2 plus 1/2, which is, look around the corner there, I don't know what 1/2 plus 1/2 is, but I think you could guess. Okay, so this little upward omega here comes out to be 1, this pi thing, which is the same as this, and that's what's weird about this one, because the slow mode frequency, and I should have arrow down on that, this is omega 0 minus that omega over 2. It's absolutely 0. That's what's going to happen, hopefully, if the demonstration that I'm about to show you here works. So let's move ahead on this one so that we have it on the screen ready to simulate. This is what it should do. Let's see if we can make it do it. Now, in order to do that, I'm going to hit this guy right here, high frequency mode, and let her rip. See what it does. Here she is. Now, what's cool about this particular thing is I'm talking about a spin vector that's lined up with the omega vector, okay? The S vector and the omega vector are sitting here on top.